Hello students, today we will discuss on the topic that is electrophilic substitution reaction. In the last class already we have discussed the mechanism of nucleophilic substitution and mechanism of elimination reaction, that is E1, E2, E1CB, SN1, SN2 already discussed. Electrophilic substitution reaction generally observed by aromatic compound because aromatic compound has pi electron clouds, so pi electron cloud easily attracted by the electrophile because electrophiles are electron deficient species. That's why they are easily attracted towards benzene ring which has electron cloud, pi electron cloud. So what are the mechanism of electrophilic substitution? If you see that almost all aromatic compounds show electrophilic substitution reaction. Addition reaction generally they do not show because the pi electron cloud is not fixed. It is revolving around the ring. That's why as the pi electron cloud is not fixed, so addition reaction is very very slow. We can say they generally do not show addition reaction, but under condition they show addition reaction. But what are the electrophilic substitution reaction? Let us discuss. We know the whole electrophilic substitution reaction. If you see, suppose let us take the example of that haloarene. If we discuss about haloarene, this is the structure of haloarene. We are discussing the electrophilic substitution reaction of haloarene. So what happens here? This is the lone pair on the halogen atoms. If you see the resonance, as it has resonance like this, if you see the structure, the negative charge is produced here and also here. If you see the resonance step by step, so negative charge generally produce this position and also if you do like this and this position. Compared to position, suppose this is your 1, 2, 3, 4, 5 and 6. If you see position number 2, 4 and 6, 2, 4 and 6, this position getting more negative charge by the resonance, and this resonance is called plus R. Why it is called plus R? Because these are electron activating group. They are supplying electron toward the benzene ring, so electron density around the ring is more. So as 2 position, 4 position and 6 position getting negative charge, so if you add any electrophile, electrophile let it be positive charge, electron deficient. So it attack at which position? Position will be, so this is your group, halogen group. It produce which position? That is ortho position or para position. So these are 2 positions. The electrophile attacking ortho position or para position. This person is ortho, this person is para. So both are ortho, this is para. So the product is ortho para substituted benzene. Okay. Then the nature of electrophilic substitution. The nature of electrophilic substitution will be affected by the nature of X. Suppose as it is a haloarene, so due to resonance, the electrophilic substitution in case of haloarene is at ortho and para position. But if you take the group that this is electron donating group, if any electron withdrawing group is present, suppose group is electron withdrawing nature. If electron withdrawing group is present, if you see the resonance will be like this. That means here produce plus charge, here produce plus charge, here produce plus charge. So electrophile will attract the position. Which position? This is one position, this is 2, 3, 4, 5 and 6. So 2 position, 4 position, 6 position getting more positive charge compared to 3 and 5. So electrophile attached to meta position. So this is the very important. What are the electron? These are called electron donating group. This G is called electron. This is called electron withdrawing group, EGG, and this is, we can say, as they are supplying electron, we can say electron donating group, EDG, electron donating groups. What are the electron donating groups? Your are EDG. EDG, electron donating groups, generally 3 are like this, greater than 2 are, then RCS2, then R like this. These are electron donating groups. And electron donating groups also observed by your amine also electron donating groups, and your halogen X electron donating groups, if you see. So these are electron donating groups. Also OR groups, also electron donating groups. So like this, these are electron donating groups. What are the electron withdrawing group? Electron withdrawing group generally that plus NR3, this group is greater than that electron withdrawing group. This one, you hear also that cyanide, then nitro, sulfuric group, like this. These are electron withdrawing groups. And also aldehyde ketone, ketone. So these are electron withdrawing groups. If this type of group is available in this position attached to benzene ring, then due to the removal of electron from the benzene ring, the electron density will be more at 3 and 5 position, that is meta position, compared to ortho and para position. That's why the electrophile attack at meta position. But if electron donating group is there, they will activate the ring. Activate means these are called activating group, these are called deactivating groups. EDG groups are called deactivating groups, and EGG are called deactivating groups, and EDG are called activating groups. These are called activating groups, donating groups, activating groups, and this is called deactivating groups. So this is the difference: electron donating groups, electron withdrawing groups. What are the position? Ortho and para, in this case is meta. But here, what are the electrophilic substitution reactions generally? Types of electrophilic substitution generally halogenation. Generally takes place in presence of halogen and one Lewis group ferrichloride, like this, aluminum chloride you can use. Then nitration is done then the presence of nitric acid and sulfuric acid, both are concentrated. Some cases direct nitric acid also used. Then sulfonation, only sulfuric acid. Then number 4, that is Friedrich-Krupp alkylation, already you know, and this is done by RX and then aluminum chloride, Lewis acid. Then Friedrich-Krupp acylation, this is also RCOX plus aluminum chloride. So here, what are the electrophiles? Here we discuss one by one. Here electrophile will be X plus. When X2 will be added with AlCl3, then AlCl3 as it is an electron deficient accept X minus. So forming X plus and AlCl3 X minus. If it is X means halogen, then product will be X plus electrophile. This is electrophile. But in nitration, what happens? NO2 plus. NO2 plus is produced. Then HSO4 minus. Then water. This is your. So NO2 plus is your electrophile. Here sulfonation is very important. SO3 plus HSO4 minus plus water. So this is here SO3 acts as electrophile. And in alkylation, very important, alkylation is your R plus remaining AlCl3X minus. So R plus is electrophile. In acylation, RCO plus AlCl3X minus. So these are very important electrophilic substitution reaction, halogenation, nitration, sulfonation, alkylation and acylation. Then what are the mechanism? How the reaction takes place? If you see, let us take one example, that formation of ortho. Let us take one example, ortho substitution. If it is a halo, suppose chlorobenzene, if you take chlorobenzene, this is your chlorobenzene. When you add electrophile, suppose halogenation, let it be halogenation. So electrophile is Cl plus. If you take halogenation, then Cl plus will be added. Nitration NO2 plus will be added. Then sulfonation SO3 will be added. So here what happens? Here chlorine, first pattern, as the electrophile already discussed, as electrophile always in haloarene always ortho and para derivative. So let us discuss the product ortho derivative. So what happens? When it will come to this side, then it will attack to this position. Then first step, this remember, first step attacking of electrophile to benzene is a red determined step. It is a slow step. Generally it is a slow step, red determined step. Then what happens? First will be Cl. Then what happens? You see, then already hydrogen is here. Then chlorine will be substituted. Then this group will be plus. It will be plus. Then like this, remaining this. So formation of positive charge. And similarly, if you see what are the resonance, it will be moved like this. What are the resonance structure? Chlorine, then H, then Cl. Here it will be plus, then like this. If you do another resonance structure, if you do resonance here, it will be like this. So plus that, then H, then Cl, like this. So now it is plus. So if you see, plus charge is forming in different carbon by the resonance. Here what happens? This up to this we can say this is called sigma bonded complex. This is your sigma complex. This complex is produced. It is stabilized by resonance. This positive charge is circulating through the ring by resonance, and it is called sigma bonded complex. Because the bond is here, you see sigma bond is produced, so this sigma bonded complex. So first step, what happens? The substrate react with the electrophile, and the reaction is very slow, and formation of sigma bonded complex, that is carbocation is produced, and it is stabilized by resonance. It is called sigma bonded complex. Then the sigma bonded complex, what happens? This sigma bonded complex, then it will lose. Suppose all these three structure can be written as like this. So plus Cl, H and Cl. So as the whole positive charge is circulating, so what happens, this H will be removed from here, it will be removed from the benzene, then it will be, this H removed will be, what happens, it is a loss of H plus. Here this loss of H plus, loss of proton, this step is fast step, is very fast step, and formation of result is your substituted chlorobenzene at ortho position. So this is the ortho benzene, ortho dichlorobenzene. So ortho derivative, chlorobenzene is the initial substrate and chlorine is added at ortho position. This is the ortho derivative. So ortho derivative. Similarly, you can do para derivative. You can do it. So here, this first step, this is the step one. Step one. Step one is the slow step, that is rate determining step, and step two is the fast step. This is step two. So if you see the kinetics dx by dt is equal to A. Only this both, that is concentration of your substrate and which one? And electrophile, E plus. Electrophile. Here electrophile is Cl plus and substrate is chlorine. So this is the rate determining step, as it is a slow step. So this reaction, electrophilic substitution reaction, depends upon the concentration of electrophile and also concentration of substrate. Both depends. If it is increased, rate also increase. If electrophile is increased, rate also increase. But second step is the fast step, is not rate determining step, and it proceeds in what? That in sigma bonded complex. That is, we can say it is a transition step. So what are the mechanism here? You can see as it is produced like this. If you diagram, if you draw, this is your energy and this is your progress of reaction. If you do, this will be the so what happens, if you see, so this is the reactant, this is your product, and this is your first step, that is formation of what? Sigma complex. This is your sigma complex is formed. Then sigma complex, so formation of sigma, and that is sigma complex. Then sigma complex, what happens? It will convert to which one? Convert to that sigma complex when loses H plus ion, it is convert to the it will be convert to that sigma bonded. Here what happens, the attacking of, here what happens, attacking of this and produce this. Here this is your sigma complex, here this is your sigma complex. Sigma complex is produced. Then sigma complex, what happens, then due to loss of hydrogen, then what happens, there will be increased energy, then going down. So this is your the graphical representation of the electrophilic substitution reaction, ES, electrophilic substitution reaction. And here first step is the slow step, second step is the fast step. Then what are the nature? If you see the nature of product, if you see ortho-para product is produced, in this case generally ortho plus para, electron withdrawing group, if generally electron withdrawing group you take, if electron withdrawing group, electron donating group, if you take electron donating group, what happens, the ortho-para ratio, ortho-para to meta will be greater than 1. The product of ortho, as electron donating group produce ortho-para both, ortho and para. So ortho-para mixture, that is with respect to meta, will be greater than 1. But electron withdrawing group, what happens? The O plus P ratio to meta will be less than 1. That means meta, the percentage of meta will be more in case of electron withdrawing group, and in case of electron donating group, ortho-para ratio is more. But it is being observed ortho will be 30% and ortho will be 20%, then 20%, para will be 30% and meta will be how much? 40%. Both 20%, 40%, 60% and 40%. But how can we increase the ortho-para ratio? Ortho percent, para percent ratio can depends upon what? The nature of the group attached. If the group is, for example, if group is halogen, if it is halogen, X halogen, if that here is suppose chlorine, bromine, iodine, if you take, then in case of what happens, here the para orthos in case of iodine, what happens? In case of iodine, the ortho percentage is more compared to this para. So ortho para ratio will be greater than 1. O by P ratio will be greater in case of iodine. O by P ratio will be iodine greater than your bromine, greater than chlorine, Here what happens? Ortho to para ratio. That means if iodine will be substituted, then the percentage of ortho will be more. If chlorine is substituted, then the percentage of para will be more. Because it depends upon the nature of group. As here, iodine, if you see iodine is large size. So what happens? The resonance, here what happens? Chlorine as it is more electronegative. As chlorine is more electronegative, so electron density compared to iodine will be less, because chlorine is more electronegative than iodine. So electron density minus I effect is more. That's why the percentage of ortho, as that is very closer to the group, so percent ortho will be less. As in iodine is less electronegative, that's why the percentage of ortho will be more in case of iodine. Similarly, you can also do that if the group is attached to, suppose benzene ring, you can take benzene ring. Suppose benzene ring containing 2R. If 2R is there, this 2 bulky group is there, what happens? Here ortho ratio will be less. Here what happens? The ortho and P by ratio will be less, because the bulky group. When bulky group attached to the benzene ring, then ortho percentage will be less, then para percent will be more. That means para will be the major product, ortho will be the what? Ortho will be the generally ortho will be the lower percentage. So you have to see the nature of group attached to the benzene. If the group attached to benzene is more bulky, then ortho percentage will be less. So here chlorine, bromine, iodine, here what happens? As chlorine is more electronegative, then what happens? Electron density electron density will be less. As electron density here, as chlorine is electronegative, then it will withdraw the electrons. As electron density is decreased, so attacking at ortho position will be less, but para position will be more preferred. That's why the ortho para ratio in case of iodine is more. That means percentage of ortho will be more in compared to para in case of iodine, bromine, chlorine if attached to benzene. But if the group is a bulky group, if 1 methyl is there, if 2 methyl is there, then what happens? The ortho ratio will be less. If number of R will be increased, then ortho ratio will be decreased. For example, if you take benzene, only benzene and toluene if you compare, suppose it is a toluene R, CH3 group, toluene. In case of toluene, what happens? Methyl group is here, methyl groups. So benzene is ortho percent. Here benzene is not a ortho para groups, but here what happens? Toluene, Then bulky group, you take another bulky group. If you see that CH attached to 2R like this, then ortho, here the ortho percentage will be less in this case compared to toluene. That's why the ortho para ratio is more in this case. Ortho para ratio will be less in this case than compared to toluene, because the bulky group is there. Bulky group is there means ortho percentage will be less. So these are the very important that criteria regarding the percentage of ortho, para and meta. One thing remember, that if the group is electron withdrawing group, if group is an electron withdrawing group, that if G is an electron withdrawing group, the product will be meta. It will prefer at meta position. If group is electron donating group, then the percentage, the ortho para percentage will be more. So it is written like this. You see that EDG, electron donating group, ortho para, total ortho para ratio with compared to meta will be greater than 1. If electron withdrawing group, then ortho para percentage with respect to meta will be less than 1. So you have to see the mechanism, how the electrophile attacking at the ortho position and para position, and which position is preferred. Where ortho, so for example, in this case para will be preferred. But here toluene compared to last one, that the percentage of ortho will be more. Percentage of ortho will be more, here percentage of ortho is less. So different types of product is formed. Ortho product and para product and meta product is formed, but the percentage will be less. Here ortho para percentage will be around 60% and meta percent will be 40% if you use the electrophile, attacking electrophile for the chlorobenzene or any dose. So this is regarding the mechanism of electrophilic substitution reaction. Next class we will discuss regarding that organic distinction of haloalkane, haloarene and other halogen derivative. Okay, thank you all.